Sinus. I've been in this with Sinus for about 12 years and been in the industry for about 24 years. I'm pleased to start. We're going to talk about modern boiling room concepts and components. I'm actually going to take my camera off because I think it'll be more of a distraction. And at this point, we'll start with the presentation. First thing I would like to do is talk a little bit about Sinus. Sinus is a full-service mechanical sourcing firm for hydromechanical, hydronics, and air, HVAC, and plumbing devices. We have been in business for over 95 years with 2 locations, one in New York, one in New Jersey. Little about what we do and how we achieve success. We like to feel that we can provide a 360-degree experience for HVAC and plumbing solutions. We have a large staff of engineers and technicians that can provide an overall view for the company. We can go in from the contractors to the owners. We can provide detailed information on installations and also equipment selection and optimizations of systems. We have 3 ways that we look at providing our 360-degree experience. One is the Hydro Source, which is with new construction, we provide equipment and advice. As you can see, some of the information, training falls along that category too, which is part of what we're doing here. Hydro Max, which is for property managers and facility managers, turnkey solutions for operate performance and extending the life of its capital equipment. And then HydroFab, which is our we can fabricate prefabricated skids and prefabricated systems that can be directly delivered to the job site quickly and efficiently integrated into the building system. And our manufacturing partners include Aquatherm, Danfoss. You can see the list here. Gould's Water Technologies is some of the finest companies in the industry. And Lochinvar is one of the ones that we're going to talk about extensively today, as well as Bell & Gossett and some of the other manufacturers. So some of the projects that we've worked on, as you can see, everything from Wall Street, a lot of major buildings in New York and New Jersey. Many of the major buildings in New York and New Jersey, we have been intimately working with both the contracting and engineering firms to help with their mechanical systems. And Bell & Gossett has been for over 50 years had the Little Red Schoolhouse, which has been the mainstay of hydronic training and plumbing and systems training for the industry since, I mean, it's been over 50 years. The schoolhouse has trained many people. Most of the people in this industry have had some training at the schoolhouse at one time or another. So with that Bell & Gossett tradition, we at Sinus continue our work to provide training and knowledge for the industry. So today, I'm going to talk about a little bit what we're going to cover. We're going to cover basic theory, that's simple hydronic theory, the components, what they do and how they work together, some piping concepts, some zoning concepts, expansion tanks and sizing, pumping and pumping options, heat loss, boiler options, control options, and water quality. Those are the subjects that we're going to cover today. So let's start with hydronics. Hydronics is the art and science of providing the right amount of hot water at the right temperature to the right area to furnish the right amount of heat or comfort to the occupants. So the key thing here is it's the right amount and the right temperature. So let me ask you a question. Just answer this to yourself. Hydronic heating systems offer the maximum amount of comfort and efficiency possible to their owners. Well, that's not really true. What is true is that when a properly designed and installed hydronic system, that system will offer the maximum amount of comfort and efficiency. So any improperly designed or installed system will have the same problems. There'll be hot areas, there'll be cold areas, there'll be large temperature swings, and there'll be inefficient operation and fuel wasting. So that's why we're here today, to learn the right way to design and install modern hydronic systems. This is a little bit of basic theory. Before we get started, we talk about BTUs all the time, but where did the term come from? Well, there was a British engineer named Thomas Treadgold. He wrote a book called Heating and Ventilation of Buildings. This book went in there, and in order to present his information, he determined what a British thermal unit was, and he defined it. And a British thermal unit is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. Now, 1 gallon of water weighs 8.33 pounds. So from that information, how do we get BTUs? Well, 8.33 times 60 minutes is about 4.998, which is rounded off to about 500. So if I have gallons per minute times a change in temperature times 500, that will give me BTUs per hour. Now, what is the delta T? The delta T is a term that we use to express the difference in temperature. That's very simple. So if I have in typical hydronic systems, we have a 20-degree delta T. More modern systems, we maybe get a 30, 35, or 40 degrees delta T. That's in some systems, if you have you may have a very small difference of temperature. When we're designing systems from the outside, we know that the outdoor temperature may go as low in New York, say to 10 degrees, and we may want the occupancy to be 70 degrees. That's a 60-degree delta T. Gallons per minute times delta T times 500 gives me BTUs per hour. So 30 gallons per minute times 20 times 500, which is a 20-degree delta T, will be 300,000 BTUs. So 10,000 is the factor that we use for 20-degree delta T. If we had 15-degree delta T, we'd use 7,500. If we had 25-degree delta T, it'd be 12,500. And then for 30-degree delta T, it would be 15,000. The key thing is that most hydronic systems, we design it traditionally for about 20-degree delta T. So therefore, we tend to use the 10,000 number all the time. How do we determine these factors? Once again, 8.33 times 60 minutes times delta T gives me the BTUs. 8.33 times 60 rounded up to 500 times 25 gives me 12.5. 8.33 times 60 rounded up to 500 times 20 gives me 10,000. The most important thing to remember is, once again, is that 20 degrees delta T is the most common factor in determining the necessary GPM to deliver BTUs. Rarely will you use less than a 20-degree delta T. Occasionally you will use more. So if you're figuring a system out at 20-degree delta T, you're pretty much going to be safe that you're going to have sufficient flow to provide heat for the space. Now you can move as much water. You can move just as much water through a pipe without creating noise. You can move only so much water through a pipe without creating noise. Now that's common sense, but it's also physics. As you know, you can't use 10 pounds of sugar in a 5-pound bag. But if you try to put too much flow through a pipe, the circulator will certainly try to put it through. But you can only move so much water through a certain diameter pipe. Another important concept is 1 psi will raise water 2.31 feet. If I had a 1-inch diameter tube and I put a pound weight on there with water on one side, and it was a U tube, the water would move up 2.31 feet from the 1 pound of weight, as long as it was inch in exactly an inch in circumference, an area. So if I had a tube with an inch in area, or say a square that was an inch by an inch, so it was 1 square inch, I put a 1 pound weight on there that was square, it would move the water up 2.31 feet. 2.31 feet, if I take the static height of any building, divide that by 2.31 to get the PSI, and I add 4 PSI, that is the proper fill pressure for that particular building. So if I have a house, I have 20 feet in height, divide that by 2.31, then add 4 to that. That's going to give me approximately 20 feet is going to give me approximately 8 PSI, or is going to give me about 8 PSI, add 4 to it, that's 12 PSI. That would be the proper fill pressure for a 20-foot building. And similarly, if I take the 1 over 2.31, is going to be 4.33 pounds. So a foot of water will exert pressure of 0.433 pounds. So the rule of thumb when sizing the maximum flow rate that will fit through a pipe without making velocity noise, the pump head will be 4 feet for every 100 feet of pipe. Okay, that's a key thing. When you're sizing a pump, the maximum flow rate that will fit through the pipe without making velocity noise, the pump head will be 4 feet for every 100 feet of piping. So if we take typical pipe sizes, a 1/2 inch pipe will flow about 1.5 GPM. 3/4 will flow about 4 GPM. 1 inch, about 8 GPM. 1.25 about 14 GPM. 1.5, 20 GPM. And 2 inch, about 45 GPM. And as you can see from the previous discussion, with a 20-degree delta T, 1.5 GPM correlates to 15,000 BTUs, 4 GPM to 40,000, 8 GPM to 80,000, 14 GPM to 140,000, 20 GPM to 200, and 45 GPM to 450,000. Basically, whatever the GPM is, multiply it by 10,000, and that'll give you the BTUs delivered. We have calculators that can help you do this. One of them, the one that I use the most, and most of us at Lochinvar use all the time, is the Bell & Gossett System Sizer. It comes in either on your iPad or iPhone. It's also an Android version available. You can get it from the App Store. Just type in Bell & Gossett System Sizer and you can download it. It gives you a much larger range of pipe sizes, large pipes and stuff like that. It includes PVC as well as copper and steel, comes in English and metric units, and handles other fluids other than water. But you can also use it using our old-fashioned system sizer wheel, which is what the app is made after, or you can also download it from Bell & Gossett's website, which I also keep on my PC all the time for doing simple calculations. So a lot of this information, like I said, is readily available and is quickly calculable using the Bell & Gossett System Sizer. If in fact you would like to get one of these wheels, you can send an if you go to Wallace-Innes's website, you can get a we will send you, if you go to www.wallacinnes.com, there you send the contact information and request a system sizer wheel. We'll be happy to send one to you. So let's talk a little bit about hydronic components. The components that we're going to talk about are the boiler, pumps, expansion tank, pressure reducing valve, flow valve, air elimination devices, and a pressure activated bypass. So let's start with the boiler. With the boiler, we have to consider, when selecting the boiler, first thing we want to do is what size boiler do we need? So our concern is the domestic hot water requirements. What are we going to need for domestic hot water requirements? How are we going to vent the unit? How much space do we have for the unit? These are the questions that we ask ourselves when trying to select a boiler for any given building. Now, we may need a retrofit. And what are the reasons for a retrofit? Well, you got boiler failure, fuel savings. With local law 97, it's also emissions compliance and efficiency. As you can see, looking at an old boiler, here you can see that with an old system, you had high maintenance costs, you have high losses, standby and surface losses, high temperature flue gases, which is basically throwing energy out into the atmosphere. There are inefficient system controls that leave you with hot and cold spots and also don't maximize the operation of the boiler. And also you have high emission levels, large NOx, carbon dioxide, and carbon monoxide. And then why do these boilers fail? Well, a lot of them just get old. You have thermal stresses and mechanical stresses. You know, every time you heat something, the metals can expand. As they cool down, they contract. Over time, it'll cause wear, small fractures, and eventually destroy or break down the metals. You can have corrosions that are caused from chemicals, either flue gas condensations or chemical contamination of the combustion air. And then on the water side, very common is scale buildup and corrosion. I mean, this is, anybody who's taken out a boiler will see that. So when do you retrofit a unit? Well, the obvious one is when the unit fails. Also, the age of the equipment, trying to get ahead of it, the boiler parts are wearing out. When maintenance costs are constantly increasing, or when you need lower fuel consumption is desired. I mean, we're looking to increase energy. We may want to switch from oil to gas or electric to gas. Or as I say, did somebody say local law 97? Is there a reason that, is there a government mandated reason why we may need to improve efficiency? And how should that retrofit take place? Well, by fact finding and investigation of the entire system, we can make a determination as to what the optimal or the best or selections and devices that'll maximize minimize the cost and maximize the efficiency and operation of the system. So we like to look for possibilities and opportunities. You can have retrofit or new construction. One of the things we look at is system water temperatures. That is the delta T. Okay, if the higher the delta T, the more efficient the system will run. If we can provide the comfort with higher delta Ts, we will then be able to absorb more energy and have the system run more efficiently. Occurrences of different loads by different times. We have night setbacks, as I'm sure everybody's familiar with. You have night setbacks and also cutting things down due to solar gain. The structure of the building, we will look for the structure of the building and see if there's opportunities to take advantage of the configuration of the building. Once again, large solar gains, minimal occupancy, commercial parts that are not really occupied, and we can look to reduce the temperature in those sections of the buildings. One of the things that we want to do is, if we could lower the temperature of the water in the system, then we have an advantage of being able to produce a more efficient heating system. So one of the things we're always looking to do is lower the temperature of the system design. We look to optimize the system by using system piping alternatives to improve the efficiency and optimize the efficiency. We can use electronic control systems to improve system efficiency, and also to integrate the systems together so they work uniformly, and you don't have one section pulling and operate. You have each section operating in unison to get the system to work in maximal efficiency. Now, integration possibilities. Let's look at first our heating system, the hydronic heating system. We have baseboard, radiators, or in-floor heating, radiant heating. You may have pool and spa heating. You have fan coils, rooftop fan coils, providing heat for various coils. Domestic hot water heating. It's a big part. In many buildings, the domestic hot water load is much greater than the heating load. And in a lot of cases, you need to design the system for providing domestic hot water. And also, when you design the system, you need to provide the domestic hot water without oversizing the regular hydronic heating system or space heating system. You may have snow melting on ramps or various walkways, garage fan coils, in-suite fan coils. You may have some buildings, you may have occupants that are using electric heaters to supplement their hair, maybe to supplement their space, to heat their space up. Small electric heaters, maybe looking to get rid of those. Or we may be looking to preheat fresh air before it goes into the system, which is into the building, and to improve the air turns. Whenever we select a system, one of the things we're looking at is what will the project save? So here's a project that we worked on, Fairfield Commons. We had Lochinvar night boilers. We do a present value calculation and looking at the cash flow method and see what happens over the life cycle over the next 25 years of the unit. And as you can see, we'll do the calculation looking at what the cash flow is and what the present value is and what the savings are. And here is, if we have Lochinvar night boilers, the total cost would be $329,000 after 25 years. Whereas if you maintain the same material, the same equipment, after 25 years, provided the equipment survives, with increased maintenance costs, lower fuel efficiencies, and lower operational efficiencies, you might be looking at a $1.35 million bill at the end of 25 years. So really, as you can see, the payback over time is typically around 5 or 6 years. You can see there's a payback where the savings, where the installation of a new system will actually provide pretty dramatic savings over the life expectancy of the units. Now you can compare that with what happens with the existing equipment versus the Lochinvar equipment, and as you can see, the two costs can be plotted over each other, and you can see that there's a huge savings, $1 million savings over the cost of keeping the existing equipment versus replacing the existing equipment. So we look at that in each one of, we look at that with many of the projects that we work on, and work in conjunction with the building owners and the facility managers. We typically like to look and see what will the return on investment be over time, and as you can see in this case, it's a 47% return on investment. And not only that, one of the things that happens over this is that the project will save emissions. Here's nitrous oxide changes over time. Here we can see carbon monoxide changes over time, and carbon dioxide changes over time. They're pretty substantial. It's almost in each case, these are at least cutting the emissions into the environment by almost by half. And yet when you look at these jobs, and you can see they speak for themselves. Here's a boiler room, and you can see what the situation was before, and here you can see the after. And I mean, it's pretty stark and pretty obvious. So one of the things is that when looking to optimize these systems, one of the first questions we have to ask ourselves is, what is the heat loss? But let's talk and say, what exactly is heat loss? Heat loss is the rate at which heat leaves the building under what conditions, and from that information, how do we size the boilers and how do we size the radiation? Now, this is an interesting chart here. What you're seeing is these are the amount of hours at various temperatures that occur in New York City. So as you can see, 72 plus degrees when we're cooling is actually, it's a lot, but when you compare it to all the times where it's less than 72 degrees or less, it's actually a great deal less. In fact, what those figures show, that the design conditions, those conditions where we're looking, which is the conditions which are set for around 10 degrees, they rarely ever occur. Okay. Cooling mode is only about 10% of the time. To design around the cooling system is actually backward. Out of 8,000 hours of heating, design conditions occur less than 100 hours. That means 99.9% of the time, the building can be heated with less boiler or less radiation. So how do we implement that concept into efficient selections of equipment? Well, you could put in smaller boilers, or you could put in less radiation, or we could lower the water temperatures. What is that? How does that work out? Well, let's take a look at a sample heat loss. Here's a heat loss of a house. And you can see here, with a design temperature of 0 degrees, the heat loss was 23,000 BTUs per hour. If we up that to 35-degree outdoor temperature instead of 0 degree outdoor temperature, that heat loss then drops to 11,700. That's more than half. A 70-degree design difference would give you, say, for example, in a house, 100,000 BTU heat loss. And that's basically the heat that's leaving through the roof, through the walls, infiltrations, and also through the floors. A 35-degree design difference will give you a 50,000 BTU heat loss. Same situation for the same building. Now let's face it, it's 35 degrees outdoors a lot more often than it's 0 degrees outdoors. So how do we size the boiler? Do we use a 50,000 BTU boiler, or do we use a 100,000 BTU boiler? And what about, so the concept is that if you look at baseboard, for example, as you can see, at 180-degree water, which is typically what we're heating hydronic heating systems at, they would put 570,000 BTUs, 570 BTUs per linear foot. If we had 130-degree water, so 140-degree water, it would produce about half as much. So if we cut the water temperature down, we've effectively reduced the output by 50%. And how do we move the water temperature from hot to not so hot? Well, one of the first ways we do it is there's an outdoor reset control. We set controls out there that when the temperature outdoors is 0 degrees, we want 180-degree water. When the temperature outdoors is 60 degrees, we want 140 degrees water. We can set in Lochinvar boilers, for example, pretty much every boiler now, that's required to have an outdoor reset control, which basically adjusts the outdoor temperature, adjusts the system temperature based on the outdoor air temperature. And that's pretty much required. And the question that we may say is that even with doing that, I mean, in the case of a simple 100,000 BTU, you're going to have one unit. But if you have a large load in a building, how many boilers do we fit in a room? And how do we make this selection? So first thing we have to do is we have to look down at the boiler turn down ratio. And the boiler turn down is the ratio between the boiler's maximum output and minimum output. And depending upon the burner's design, it may have a turn down ratio between 5:1 and 10:1 or even higher. For example, the Crest boilers have a 25:1 turn down ratio. A 5:1 turn down ratio means the boiler's minimum output load is 20% of the boiler's full capacity, or 1/5. Okay. In that case, a 100,000 BTU boiler would be able to put out as little as a 20,000 BTU load. Now, if we're selecting multiple boilers in a building, do we want them all the same size? Well, in most cases you do. It makes it for simplicity of operation, and also so the controls will often require that. Lochinvar does offer an interesting option, which I'll speak a little bit about. We do a thing called front-end loading. So in this particular case, what you see here is 2 plus boilers, which provide the majority of heat over there. But when you get to that 0-degree day, which happens very infrequently, there's no need, there's no requirement. There's no requirement to have a condensing boiler. We can put a non-condensing. Here you see a copper fin with these 2 condensing boilers. These boilers will operate around 92, 93, 94, 95% efficient. This will operate at about 85% efficient, because that water temperature, going back to the information that we had before, those water temperatures are only going to drop when the outdoor temperature is relatively high. So if it's warm outside, if it's warmer outside, the water temperature is going to be pretty low, and you're not going to need this condensing boiler will not come into play. As the temperature starts as the temperature outdoors starts to drop, the water temperature starts to increase. These boilers have difficulty keeping up the demand. It'll then go into condensing mode. The water temperatures are going to get higher. This is going to leave condensing mode, and it'll turn this boiler on because it doesn't really matter. So it's a clever way Lochinvar has their systems. Their smart systems can automatically integrate this information it can do it automatically for them. Now, also one of the things is that you have to consider is when you're selecting a boiler, do you oversize it, and why? Some of the big concerns, for example, in a house, a simple house, you may have typically a building will have 35 BTUs per square foot. So if I have just a simple 1,000 square foot house, that'll only have a 35,000 BTU load. Yet if I have a single shower in that 1,000 square foot house, each gallon per minute, and a typical shower uses about 2.5 gallons per minute. Each gallon per minute will use about 40,000 BTUs. So I will need 100,000 BTUs to satisfy the domestic hot water load, yet I only need 35,000 BTUs for the heating load. So one of the things that we have to consider is often we are designing for the domestic hot water load, and then we're also adjusting to we're making this balance situation to get the hydronic heating load to operate in an efficient place. Now, once again, we said 35,000 BTUs for the heating load, but that's on the coldest day of the year. Most of the time, this thing is going to be running about half of that, which is 17.5 or 15,000 BTUs. So ideally, I'd really want a boiler that would put out about 10,000 BTUs, yet could go up to about 100,000 BTUs. So when there's a domestic hot water call, it can produce 100,000 BTUs. When there's a heating call at 10,000 BTUs, I'm still able to operate in that range. Now, the other thing is let's just magnify that, and let's magnify that in a much bigger building times 100. Say it's instead of it's 350,000 or even 3.5 million, for example. At that point, we want to select boilers where we can have a multiple of boilers where we can continue to modulate down to supply small heating loads, because you're going to have a much larger building. Certain areas are going to have solar gain. There'll be no call for heat over there. Other areas will be colder and chillier. There will be a call for heat over there. So that deviation will be even greater. So at that point, we want to choose a number of boilers to compensate to also provide the domestic hot water load. For example, if it's an apartment house, it's going to have a large, high domestic hot water load. If it's a office building, not so much. There's what are there? A couple of showers and a few sinks. You don't have a shower in every apartment. So you'll have a much lower domestic hot water load. So you really have to look at the building itself and what the demands are of the building. Figure out what if you're going to use the boilers to provide domestic hot water, we need to balance that out in conjunction with the heating space load. And that's something that we look to optimize with we are available. We do this often, and we are available to help in that process. Now, Noble, let's talk a little bit about what Lochinvar offers and we at Wallace offer as boiler options. We have in residential situation, we have a Noble fire tube combi with 3 units, one at 110,000, one at 150, and one at approximately 200,000 BTUs. Now, these units provide both heat and hot water. They have, I believe, a 10-to-1 turn down ratio, so you can get, if they work in conjunction, if, for example, a 200,000 BTU unit can actually run 2 showers simultaneously. These are all designed, engineered, and assembled in the United States. They have a small footprint. They're wall hung, a relatively small footprint with a 10-year heat exchanger, 5-year parts warranty. And the Noble not only comes with a combination unit, it also has 4 models in a heating only unit. An 80,000 BTU, 110, 150, and a 200,000 BTU. Again, designed, engineered, and assembled in Lebanon, Tennessee. All made in the USA. Same dimensions, same warranty, 10 years. Heat exchanger, 5 years parts. We also have the night boiler line. So we have the residential line, which is the KBN, with sizes from 80 to 285,000 BTUs. The night KHB XLs, they go from $399 to $1 million. Also the KHBs from 55 to 285, and a wall hung unit from 55 to 399, all designed and manufactured in the USA. We also have the fire tube unit for light commercials applications. They have a 400, a 500, a 600, a 725, and an 850. These units have certain advantages over water tube units in the sense that you can use full flow. You can also common vent these units, and you can also have full flow. In other words, you do not need a pump for each individual boiler. You can have one system pump, and they have very low head loss through the boiler, and you can use these boilers with a full flow pump. For other light commercial applications, we have the brand new Night XL, 400,000 BTUs, 500,000, 650, 800, and 1 million. Now this unit, you pretty much need a pump for each individual boiler. They need to be piped, what's called primary, secondary, which we'll talk about a little later. And they also have venting. They can also be common vented in up to 150 feet of vent, total equivalent length. What that means is that that's 5 feet for every elbow, 2.5, 3 feet for every 45. And so you measure the length from the vent through the termination, and it can be up to 150 feet. The Crest units, these are our largest units. They come from sizes of 750, 1 million, 1.2, 1.5, 1.75, 2, 2.5, 3.5, 4, 5, and 6 million BTUs. So if you look at Lochinvar's boiler offering, they have everything from a 50,000 BTU small wall hung boiler to a 6 million BTU fire tube boiler. These units come with all kinds of features, including integrated communications and wireless communications, and they can do them full flow. You can common vent them. These are very powerful top of the line commercial units. Well, we've talked a bit about boilers now. Let's deviate this conversation and let's go to hydronic components, and let's start off with the pump. What does it do? How does it work? How do we size it? And what are our options? So the first pump we're going to talk about is the most common pump that you see in a house and you see all over the place. Those are wet rotor pumps. Okay. The pump effectively moves water heated by the boiler around the system to and from the radiators, fan coils, baseboard, and radiant floors. Consider the pump, the flow rate as the train that heat travels on. And it's like the commuters on a train. They get on the train at the boiler and they hop off at the radiators like commuters would get off on a train. The slower the water moves, the greater the delta T. The longer it's out there, the more heat gets off the train. Okay, also talking about the pump and how it works. Centrifugal pumps use a spinning of the impeller to give velocity to the water. This velocity is captured in the volute and it creates a pressure difference between the inlet and the discharge of the pump. Centrifugal pumps, they don't actually suck water. What they are is they're a change of pressure device. And high pressure will go to low pressure, and that's what makes the water flow. Water comes in through the eye. It goes out through the centrifugally is forced out through the volute. And then the force is measured in feet of water. Basically 2.31 feet is 1 PSI. So typically we talk about the pumps in feet of head. Looking at a cross-sectional picture of this, you can see a wet rotor pump. You have a motor, you have bearings at the top. And if it's a multi-speed pump, there's a speed selector, and there's the impeller. The pump, you have wet rotor pumps. And I want to show you a little video which is excellent at explaining what goes on here. So take a few minutes and you can take a look at this video. It really explains it well.
Have you ever wondered how a circulator moves water in a system? Today we're going to cover these topics and more. These devices are actually very simple when you break them down. They are made up of separate parts. The volute is the body of the circulator. It is where the water enters and leaves the circulator and is the home of the impeller. The impeller is the part of the circulator that spins, slinging water away and creating the delta P, or difference in pressure, when the motor is energized. The motor is the electrical device that is connected to the impeller by a shaft and is responsible for turning the impeller. It's good that we know the anatomy of a circulator when we try to understand how they work. This image represents a circulator in a closed system. Most circulators will have test ports on the suction and outlet sides of the volute. But how do I know the suction from the discharge side? There's actually a very simple method. If you look at the bottom of the volute, you'll notice that one of the sides of the circulator is piped directly to the center of the body. This is always the suction side of the circulator. We know this because the impeller that is housed inside the volute begins to spin, and it creates a Venturi effect. You could imagine this as a mini hurricane inside the body of the circulator. The pressure at the center of the impeller drops, and the pressure on the outside of the impeller rises. This creates a delta P, and Mother Nature takes over from there. In nature, everything seeks equilibrium. So the higher pressure we have just created seeks out any lower pressure. The suction side of the circulator provides just that. This means the pressure coming out of the discharge side of the circulator seeks the suction side. And since we are in a closed system, it has a direct path back to the circulator. And now we have flow. It's really that simple. But how much flow are we dealing with? Do I need a fancy flow meter to determine flow? No. All you need is a pressure gauge and a pump curve. A pump curve is a chart provided by the pump manufacturer. This chart shows feet of head on one side and gallons per minute on the other. In the middle of the chart, you'll see one or more curves. These curves represent the impeller size of the circulator. Some charts will have multiple sizes shown on a single chart. Some charts will only have one curve. When reading pump pressure, you should only use one pressure gauge to read the suction and the discharge pressures. Different gauges could give you different readings because they may be individually calibrated. Attach the gauge to the suction side of the circulator and take a pressure reading in PSI while the circulator is running. Let's say we take a pressure reading on the suction side of the circulator while it's running, and it's 10 psi. We then take a pressure reading of the discharge side of the circulator while it's running, and we have 18 psi. We then subtract the discharge from the suction. 18 minus 10 equals 8 psi. That is my delta P. Now I have to convert this to feet of head by using the constant. 8 times 2.31 equals 18.48. We can round this up to 18.5. Now we find 18.5 on the foot head side of the curve, and we make a mark. Then we draw a straight line from this mark toward the impeller curve. Once we contact the curve, we change direction, and we start heading toward the GPM side of the curve. Your GPM is determined by the point where the line intersects the GPM side of this curve. Also, just for your information, there is a constant for converting feet of head back to PSI. This constant is 0.434. So multiply feet of head by 0.434 to get PSI. Wow, we just did a little math and nobody got hurt. It is important to know how circulators work if you want to understand how flow is controlled in the system. Hopefully, you now have a better understanding of how that all works.
Tony, if you could hear me, your sound is off. No one can hear you.
Thank you. Sorry about that. Let me go back a little bit. Take a look at hydronic components. The pump. The pump is like a, let's see if I can go back one more here. Okay. The pump. How do we, when we're looking to size a pump, there are two components. The BTUs tell us the amount of flow that we said before. We took the amount of BTUs divided by 10,000 on a 20-degree delta T, and that told us the flow. If we have a newer condensing system, we may want to use 30,000 BTUs. We may want to divide by 30-degree delta T. We may want to divide by 15,000. How much resistance does a pump have to overcome to get the water where it needs to go? So system flow is like a Ferris wheel. The weight of the water going up is equal to the weight of the water going down. And the pump needs only to overcome the friction of the system. So as you can see by just looking at this image, the weight of this water pushing this way is equal to the weight of this water going that way. And it's really only at this center point that it needs to overcome the system. We only need enough energy to overcome the resistance at this joint here, which poses the question, which building will get a bigger pump? Well, if you look at these two buildings, really, it doesn't matter. If we push the water up this building and it comes back here, the only thing it has to do is overcome the piping in the building. The same is here. The pumps that are required for these two buildings are identical. So how do we calculate the required pump head? First thing we do is we measure the longest run. That is the point from the boiler to the furthest piece of radiation. We measure that distance and we add 50% of this for fittings. We multiply that times 0.04. Remember, we wanted a velocity. If we had 100 feet of length, and we multiplied it by 0.04, that's going to give us 4 feet per 100. And that would be the required pump head. Here's a simple example. If we have a zone with 50 feet of 3/4 inch baseboard rated at 160 degrees F, and we have 50 feet of additional piping leading to and from that baseboard, 25 feet one way, 25 feet back, okay, that's a total of 100 feet. So 50 feet times 480 BTUs per foot is 24,000 BTUs. 24,000 BTUs divided by 10,000 is 2.4 GPM. There's our flow. Now, the length, we have 50 feet of baseboard, 50 feet of piping. That's 100 feet total. And we wanted to multiply that by we wanted to increase it by 50%. That gives me 150 feet. And again, we multiply it by 4 feet per 100. That's what we want for the pressure to make sure we eliminate velocity noise. So 150 times 0.04 is 6 feet of head. So for this particular baseboard loop, we need 2.4 GPM. We need to deliver 2.4 GPM at 6 feet of head. Pretty simple. Once again, just take we take the total amount of radiation in BTUs, divide that by 10,000 if it's a 20-degree delta T, and then we get 50 feet of baseboard and 100 feet total, multiply it times 1.5 to get 150 feet, and times 0.04 once again because we're looking for 4 feet per 100. So the pump that we needed to deliver is 2.4 GPM at 6 feet of head. You can see if we plot it on the curve, you can see we're above number 3, but we're below number 1 and number 2. So basically we could use number 1 and number 2 to provide the flow for this particular loop in either case. And as we look, you're going to see these pump curves. This is a sample pump curve for the wet rotor NRF 2233 and an NRF 9. And here's also pump curves for 3-speed pumps, for the NRF 25, 36, and 45. In general, every pump curve will have the flow of head on the left, gallons of minute on the right. What's also interesting is that if you use, for example, Bell & Gotz's system-wise software, which is covered with another class, but I highly recommend you take a look at it. If you just go to Bell & Gotz's website and under their system selection software, they have a product called system-wise. You can select pumps, put the flow in the head in, and they'll make a selection for you, and they will provide the curves for that particular pump. And then with the flow and head information, it'll give you a system curve. So the system curve, which is sort of a quadratic or parabolic curve, will intersect the actual pump curve, and that's the actual operation point of the pump in the system. Let's take a look at what kinds of pumps we have. We have oil. A lot of the old pumps were oil lubricated pumps. Those are like the Series 100 and the HV pump. Their components were simply a motor, a coupling, bearings, shaft, seal, and an impeller in the loop, inside of a loop. And these pumps these oil lubricated pumps have been around a long time. They're sort of last year's technology. A lot of people put them in still because they have, in retrofit situations, they know they're going to fit, they know they work. But in many cases, that oil lubricated pump can be replaced by a permanently lubricated pump. These PL pumps, PL standing for permanently lubricated, are offered in a wide variety. There are many different selections. Here you can see the curves on them. They go from everything from over 50 feet of head all the way out to 130 GPM. So there's a wide selection and a wide variety of these pumps that Bell & Gossett offers. In many light commercial applications and some commercial applications and hot water recirculation applications, these pumps are the ideal solution. They're substantially less money than those old 3-piece pumps. They require a lot less maintenance. They are repairable in the field. As you can see, the seal is repairable. There are bearings, a dry motor, and a rotor, and an impeller. If the seals are field replaceable. Other pump options include, for larger systems, the vertical inline pump, which is a Series 80 pump. What more and more people are using are these XL pumps, which can give you flows up to 275 GPM. Series 90 pumps, which are closed couple pumps. These go up to 250 gallons a minute. Series 60 pumps, which have a coupler and a bearing assembly. These are flex couple pumps. They go up to 250 gallons a minute. And then you have end suction base mounted pumps. So these are all the inline pumps, and then we have these end suction base mounted pumps. The most popular one is the 1510, which can have flows up to 4,500 gallons a minute. The 1535, which is the closed coupled version of the 1510, that goes up to 1531, up to 2,500 GPM. And the 1532 also, which goes to 2,500 GPM, which is basically the 1531 with a footing and a modified volute to make it an easier footing. And then they have these smaller 1535s, which are usually used in cooling applications, small cooling applications. They go up to 250 GPM. In addition, on end suction side, we have multi-stage pumps that can go 120 GPM with these multi-stage pumps can go up to 525 feet. Horizontal split case pumps, where the suction is on both sides, these can go up to 300 gallons per minute. And then Bell & Gossett's top of the line, the VSX series, which are also split case pumps. They can go up to 15,000 gallons per minute. So as you can see, everything from the smallest circulator to some of the largest buildings that you can see can be sourced by Bell & Gossett. We're always at Wallace Ennis happy to provide you information, pumping, and try to optimize your pumping solutions. As a matter of fact, my next stop right after this class is to go into New York City Housing Authority and help them come up with some selections for all pumps based on what they do, what are needed there. And once again, like I said, if you have any situations like that where you need help in pumping selections or boiler selections, you can always reach out to Wallace Ennis. We're always here willing to help. So let's talk about some of the newer pumping options. And what primary to that is electronically commutated motor pumps, ECM pumps. Now, the difference is with these pumps, they use permanent magnets. There's no shaft, no seals or bushings, and there's only one moving part. So here you see an ECM pump. You have the volute, you have magnetically centered spherical impeller or rotor, a stepless speed motor, and a high efficiency ECM motor. These electronically commutated motors, what makes them different from standard motors? Well, the first thing is that these motors the motors themselves will look similar from the outside as your standard induction motors, but inside they're very different. The construction is very, very different than it is on the outside. When you compare the two, you have an AC induction motor, sometimes called a split capacitor motor. There is no permanent magnet in the rotor. The stator coils, that's the part that stands still, those create a magnetic field which induces current into the rotor. The rotor then current that interacts with the rotating magnetic field, which causes the rotation of the motor. Because the magnetic and electric fields are not perfectly in phase, there's a slip there, and there are current losses between the magnetic field and the electric field, and that is wasted energy. And there are greater current requirements, and there are greater current losses. They can be pretty substantial. especially in the older pumps and larger pumps. It can be very substantial. In electronic commutated motors, you have a permanent magnet rotor. The permanent magnet rotor grabs onto the rotating stator magnetic field. So the stator still is going to have magnetic field going around it. And the permanent magnet is captured along with that and starts the rotation. The rotation is controlled by a microprocessor, and that keeps the stator current. There are sensors in there, and it keeps the stator current in phase with the magnetic pole on the rotor. So you can eliminate that slip. The current requirements drop, and you have much greater efficiencies. In addition to that, you also have much more, because you have a microprocessor controlled information, you have much more control over the motion of this pump. You know, it's not just putting 60 hertz in there and see how many poles you got, and that's how fast it spins. In this particular case, you can actually have a stepless motor and continuously move the pump in a continuous varying speed. As you look, the motor is a permanent magnet. Commutation is the process of pulsing the power on and off to create a rotating magnetic field in the stator. That's the part that stands still. As you can see in this little video here, what's going on is you see the poles, the north and south poles, as it indicated, is red and green. And as the different stator sections turn on, it's pulling the permanent magnet towards it. This has a great deal of efficiency, and like I said, there are sensors that can monitor it to keep the units in phase so they operate efficiently. So when looking inside an ECM pump, your motor rotation, you have an electronic driver which is required for the commutation of the rotor rotation, and the controller energizes the stator wire in a specific sequence to facilitate proper rotation. That's what makes these pumps very different, and they're much more efficient. For proper rotation, the controller must determine the rotating position via a sensor or some other means of positioning. Here's a cross-sectional view of Xylem's unique spherical rotor design. Here you can see the permanent magnetic rotor. It's the impeller, the wall flow is coming in this direction. It's the same principle of a centrifugal pump. It's the only thing that's really changed is control of the motor here. Here you can see the axis with the bearing and support system, stator windings, and then you have your PC board and your driver. So even on the outside, even though it looks similar, in reality you can see the insides are markedly different. So ECM pumps, when we talk about them, well, when we talk about efficiency in general, really that is the desired output divided by the necessary input. So one of the things that we talk about here is the distribution of efficiency for a heating space system. And the distribution efficiency is the rate of heat delivery divided by the rate of energy used by the distribution efficient equipment. So if we have a system that delivers 120,000 BTUs at a design load condition using 4 circulators used at 85 watts each, the distribution efficiency of that is 120,000 BTUs divided by 340 watts would equal 353 BTU per hour per watts. Well, what does that mean? Well, is 353 BTU per hour per watt, is that good or bad? Well, you have to compare it to something. And so let's consider a furnace blower, which operates at 850 watts and delivers 80,000 BTUs per hour. That delivery efficiency would be 80,000 BTUs per hour divided by 850 watts is only 94 BTUs per hour per watt. So really, we've improved by approximately 3.5 times greater, almost 4 times greater than a forced air system. So as you can see, hydronic systems are dramatically superior to air for heat delivery. Moving the heat around in water is a much more efficient means than moving air around. But is there really room for improvement? Let's take a look at this particular house here, and you look at the inside, and you can see all these pumps lined up like that. And these are all these pumps are standard wet rotor pumps that have maybe 85 watts of efficiency. See, these circulators actually consume this heating system. It's a 10,000 square foot house, and they had 40 circulators consuming 90 watts each. So the design heating load was 400,000 BTUs per hour. So the distribution efficiency was 400,000 BTUs an hour divided by 40 by 90, which is 111 watts per hour. 111 BTUs per hour per watt. 111. So as you can see before, we were at 353. The forced air system was a little bit over 90. Here we're at 111. We're in the same magnitude as that forced air system. You know, we're really not much better than the 94 BTUs per hour per watt. So yes, if we substitute these smaller EcoCirc pumps, these things draw as little as 10 watts. Often they'll be drawing like 14 watts. So you get almost a 10 times improvement in efficiency. And as you can see, if all of a sudden, if we have a 10 watt pump, 40 of them is only going to give us 1,000 BTUs per hour per watt. So our efficiency has dramatically increased. So from those simple numbers, we can see that ECM pumps works. But what are available and when can we use them? So let's just take a look at what are offered for ECM pumps. Our biggest offering now is Xylem and Bell & Gossett offers a new product called the 2018. It's a maximum of their numbering system is pretty simple. The number on the left is the feet of head. The number on the right is GPM. Just think of it like the chart. So the EcoCirc 2018 puts out a maximum of 20 feet of head or a maximum of 18 GPM. So that'll be 20 feet of head at much less than 18 GPM or 18 GPM at much less than 20 feet. The maximum power for full load is 70 watts. And these also once again, remember there are sensors in there. And because there are sensors in there, there's a variety of control on this. You have a microprocessor built in by definition. So we can now control it for proportional pressure, constant pressure, or adjustable speed control. Proportional pressure means that, for example, if zone valves were to go on different systems or Danfoss valves, the pressure would change, the flow will automatically reduce. It'll reduce proportionally to changes in the pressure. Constant pressure means it'll maintain a constant pressure all the time, adjusting the speed, or it'll set the speed and maintain the speed regardless of pressure, maintaining the same speed. They operate for both heating and cooling systems from 14 to 230 degrees F. They have a system protection, they have an integration protection system. They have air purge. It's the first thing when these units turn on, the first thing they do is they look to purge air to remove any air trapped in the pump. And they have one knob and a multicolor LED for easily reading. And they have a multicolor LED as one option. There's a regulated as 2018 and the 2018 Plus. The 2018 doesn't have the display. The 2018 Plus does. Each one is also included with a check valve. And if you're using them for cooling or heating, you can also comes with an insulation shell included in the box. The EcoCirc 2018 Plus, that comes also with Bluetooth capabilities. So you can actually communicate via Bluetooth. It can take a 0 to 10 volt input on all of our B&G pumps. They all put out a proportional. Once again, I said sometimes they'll have say a 10 to 1 turn down. So if I have 100,000 BTUs and I want 10,000 BTUs out of 100,000 BTU boilers, it'll be 1/10. In that case, there's a 0 to 10 volt output. That output would actually put out 1 volt. If it was putting out, say, 50,000 BTUs, it will put out 5 volts. And that 0 to 10 volt input can be used to drive this pump. And so I'll talk about later, there are big advantages to that. There's also, you can set it for temperature. And also it has a thing called eAdapt, where it'll auto learn what your system is needing, and it'll also go into night mode, and it'll look for its optimal point based on what the demands are made on the pump. And once again, it also has a digital display, which can show you both the feet of head, the GPM, and the power usage in watts. Show you feet of head, it'll show you GPM, it'll show you watts. Here you can see sample curves. Once again, the proportional pressure curve, the constant pressure curve, and the fixed speed pressure curve. Now, we're not just limited to a small unit that goes from 20 feet of head to 18 GPM. We have much larger ECM pumps. And these units also feature electronic commutated motors. There are 13 models up to 375 GPM, including 3-phase units. There are 4 control modes: proportional pressure, constant pressure, constant speed, and has an automatic night mode. These units come built in with Modbus and BACnet communication. They can communicate with a laptop for RS-484 connection. And the EcoCirc XL is a high performance pump that it takes efficiency to advanced levels through the use of ECM permanent magnet technology. It has state-of-the-art hydraulics, advanced motor design, and truly intelligent controls. There are all kinds of connections on there you can use. You can use parallel. You can pump these units in parallel. You can deliver double the flow by having them talk. They communicate with each other. They will deliver the right performance across a broad range of head and flow requirements due to it's basically a built-in variable speed, variable frequency drive. They come in cast iron, sorry, it says bronze body, but that's not correct. It's actually stainless steel pumps, and they're used for heating, cooling, and potable water applications. Here you can see the range of the units. They have high head units putting out up to 70 feet of head and up to 150 GPM in those units. And then they also have high flow units, which will put out for these smaller units that'll put out from 15 up to 40 feet of head, all the way out to 275, actually go out to 375 GPM. Those would strictly be on 3-phase units. Taking a look at the internals of this pump, what you see here is that it comes with the self-flushing membrane. It restricts abrasive particles. There's a high temperature EDPMO ring, stainless steel shaft. The pump housing will either be cast iron or lead or stainless steel. All the wetted parts are 304 stainless steel. So once we change the volute, the unit's already a stainless steel device ready for potable applications. The impeller is a glass-filled polyethylene sulfur, or it comes with 3/16 stainless steel, depending upon the unit. And the motors are ECM permanent mode. The electrical connections you can see are up here, and the displays. Those 4 modes are available from the display. In addition to, you can also see the GPM, the flow of head, and the power consumption too. And the RPM also can be shown too, so you can see the actual speed. The benefits of the EcoCirc XL, besides having the electronically commutated motor and an integrated variable frequency drive, you have infinite speed regulation. Like I said, you have 4 modes which are available from the front curve, from the front controls. And in addition, you can also use an RS-45 cable, and you can get delta P, delta T, or constant temperature controls as well. You can wire it for 0 to 10 volt input. It'll provide, and like I said, from the front, it's constant pressure, constant proportional pressure, and constant curve. Most of the time, you're using proportional pressure or constant speed or constant temperature. Basically, it has a temperature sensor inside it. It'll actually, you can use this in potable applications as a this device has effectively a built-in aquastat in it. It has nighttime setback features, so put the pump in sleep mode during low or no load conditions. There really is no specialized programming to commission these pumps. Much of the data is adjustable from the interface panel. If the unit is not aligned, you can rotate the motors 90 degrees for easy access to the data display. The illuminated display makes it visible even in dark areas. It's very good for new and retrofit installation and for energy upgrade applications. The PL series, the 3-piece boosters, the series of 90 products are easily interchangeable with these models. Flange to flange connections are pretty much, in many cases, of the same size. So they're pretty standardized depending upon the flow rates and the size and the connection size. Let's take a look at the modes of operation. Once again, we have constant pressure, proportional pressure, constant curve, and night setback. Typically, like I said, in most cases, you're using proportional pressure and constant curve applications. In constant pressure application, it means the constant differential pressure at varying flow rates until max speed is reached. Desired pressure can easily be set by the unit user interface. It has a default operating mode. It's sensorless. It uses an algorithm, and it's recommended for use in systems that have small or constant pressure losses. A good example would be radiant heating and cooling. Excuse me, I went the wrong direction here. Proportional pressure continuously adjusts based on the flow rate. The pump head will decrease as the flow rate decreases. Maximum pressure is easily set from the pump interface. There's a sensorless algorithm or an external delta P, or you can use an external delta P sensor. You can add on. They offer additional temperature sensors and pressure sensors if desired. It's recommended for use in systems when pressure varies with flow rates, as in hydronic systems using zone valves. Constant speed and constant curve. The pump speed can be set to maintain performance. The pump will maintain a fixed speed at any flow rate. Pump head increases as the flow decreases. Speed set point can be programmed for the user at the pump user interface. Constant curve is great when used for primary or boiler loop or in primary secondary hydronic systems. Constant temperature. The pump will vary the speed to maintain temperature. It has an internal or external temperature sensor. In most cases, it already comes with an internal temperature sensor. You could add an external temperature sensor and program it to use that external temperature sensor. Or, as you'll see later on, you can actually have a delta T mode when you add the external temperature sensor. You can use constant temperature. It can be used to maintain zones supply water temperature. Not only that, it can also be used in potable applications as effectively as an aquastat. In differential temperature, in this mode, the pump maintains a constant differential temperature at any flow rate. It'll use an internal and requires an external temperature sensor. The differential temperature can be used to maintain the desired delta T in a zone to better control the return water temperatures and make sure the delta T's are maintained to maximize heat delivery. Controls adjust the differential pressure. You have another control mode, proportional pressure / temperature. Controls address the differential pressure set point as measured temperature varies. It requires an internal or an external temperature sensor. It will require an external delta P sensor, and it's recommended for use in systems with varying supply water temperatures. Night setback. Pump response to night setback is controlled by other means in the system. It reduces the pump power consumption to the heating load is not requirement. A good example is evenings and nighttime. I mean, it's when the loads are lower. It's typically used in conjunction with, it's used in conjunction with constant pressure, proportional pressure, and constant curve settings. When it's those settings, you can set the night setback. Now this is part of what's really cool about these pumps. They have 2 pump operating modes. It's a simple connection. You can have backup operation where only the lead pump runs while the second pump remains off and only turn on if the lead pump fails. What more common is used is alternate operation. Only pump runs at a time for a 24 period, after which point it will power down as the other pump comes on and begins pumping. In case of pump failure, the other pump takes over. So you have coverage and you have alternation between the two. That's our most common application. You can also have parallel application, where the leader pump tries to satisfy the demand. And if it can't satisfy demand, the follower pump will turn on to run in parallel with the leader at the same set point. This operates really only in constant pressure mode. And then you can have forced parallel operation, where the leader and follower run together at the same speed to meet the demand. And the interface, to get these interfaces to work with these EcoCirc XL pumps, can either be they have a 4 to 5 input, and that wires into a LabVIEW application, which is free and downloadable, free on the, we can provide that to you. I think it actually might be on the Bell & Gosset website, but either way, if you need it, we are happy to provide it to you. It's free of charge. And if you can also include, turn that person off. There also is a wireless chip that can be put in, and then what it does is it becomes, you use your web browser, and you can use your iPhone, for example, link into it and then control it directly from your web browser. There's really no special software. Once you link it, once you log on to it, it comes up as a hotspot. Once you link to that hotspot, you open up the web browser and you can have all the controls that you would get regularly from, say, the RS-485 connection. So one of the things with ECM pumps, an important point of ECM pumps is that, you know, when you have a modulating boiler, generally speaking, most applications are using a fixed flow pump with the modulating boiler. Here you can see a 500,000 BTU modulating boiler with a 5-to-1 turn down ratio, okay? And we have a fixed flow pump, which has been set for a 20-degree delta T and at 100% firing rate. So at 100% firing rate at 93.3% efficient, its output is going to be 466,000 BTUs. You'll have a 47 GPM flow rate, and the delta T will be 20 degrees. Now, if the flow rate if the firing rate drops as the heating load is starting to be satisfied, and the firing rate starts to drop, the flow rate is maintained. So the output, say when it gets down to 80% is 373, we still have a 47 GPM flow. The delta T goes down to 16 degrees. At 60%, the delta T will go down to 12 degrees. At 40%, the delta T will go down to 8 degrees. And at 20%, the delta T will be only 4 degrees. Now, if we could vary the flow proportionately, what would happen is that at 100% rate, we would still have we can maintain a 20-degree delta T all the time. So what's so big deal? What does that mean? Well, let's think about that. The key thing is that when you have a modulating boiler, to operate in condensing mode, you need to have the return water temperature below 140 degrees. So if I'm going out at 150 degree water temperature, and I'm only returning with a fixed flow pump at 4 degrees, I'm coming back at 146. At 146, I'm no longer condensing. If I have 150-degree water coming out and I'm coming back at 20-degree delta T, I will then have 130 degrees back. I will condense over the entire firing rate of this boiler with a variable speed pump. This is so pronounced that on the residential boilers, Lochinvar has now integrated a variable speed pump that's controllable as standard equipment. Now on commercial boilers, they don't provide a pump because they really don't know what your delta T's are, what your flows are going to be. Those need to be selected, which once again, when you have that, we're here at Wallace Innes, we're happy to help you with that selection. But what's really key here is that if you use a variable speed pump, you can stay in condensing mode almost all the time. That's not going to be the case if you have a fixed speed pump, as you can see. I mean, the reality of it is that if we had 150 degree water temperature, once we get below 50% firing rate, we are no longer condensing. Okay, let's go to our next component. The next component is going to be the expansion tank. What does it do? How does it work? How do we size it? And where do we put it? So what does it do? If we raise the temperature of water in a heating system from 40 to 180 degrees, that adds about 5% more water simply by thermal expansion. The expansion tank's job is to absorb this thermal expansion. It provides a spring to maintain the minimum pressure set in the system. Keep in mind, unlike air, water does not compress. So the expansion tank, here's the expansion tank before insulation. We put in the system's initial operating temperature, and then the maximum pressure of the temperature of the fluid, which is typically going to be when it hits its maximum temperature. So the air and the water pressures must match before the system is filled. Okay, we need to set, before you connect it to the system, you need to set the pressure inside the tank on the air side before. That's critical. There's a Schrader valve, like a little Schrader valve on the bottom, and that's where you set the pressure before you install the expansion tank. And when it comes to sizing, there are a number of ways to do it. Basically, Bell & Gossett has we have a program that you can use, or really you can, in smaller systems, you can just use this simple chart. This chart assumes a fill pressure of 12 psi, relief valve set at 30 psi, average system temperature about 200 degrees F. If the temperature is lower, you're going to probably have a smaller tank. And these tend to be, you have to understand one thing about, we're looking to absorb the expansion of water. So as I like to say, you can't have too much expansion tank. And expansion tanks relative to other components are not that expensive. When in doubt, you always want to go larger on an expansion tank. You have nothing, it's not going to cost a great deal of money. And if you have to start changing things and going back, or it starts to blow relief valves, it's not worth the aggravation. The cost difference between a 30 and a 60 is not that much money. And when in doubt, you pretty much always want to use a larger expansion tank. And these numbers here are very forgiving. This information is in a catalog. During the expansion section of the catalog, if ever anybody needs it, it's called I call it the 850. It's the System Component Catalog by Hydronics Residential Products. Just contact Wallace Innes. If you go to the website and just send an inquiry, ask for a component catalog, we'll be happy to send you one. There are other kinds of expansion tanks. Sometimes you'll see an expansion tank that looks like this. That's a compression tank. Most of the time, what you see is one that looks like this. This is a bladder tank. These are what's put in mostly now. These are older systems, and usually, even if these are in there, they're going to be replaced by this. And you can also get some pre-charged, some commercial pre-charged tanks or some diaphragm tanks. The bladder tank, as you can see, basically pretty simply, it just is a bladder inside a tank to hold it. The bladders are full acceptance. The volume of the fluid in the bladder that it can hold is equal to the volume of the entire tank shell. There are low acceptance bladders that are limited acceptance. The volume of the fluid in the bladder can hold is less than the steel shell. They're usually used in applications where safety and system pressure is a large concern. Compression tanks, as you can see what they are, is they're just regular tanks with air and water. 15 sizes available. They have custom tanks. Honestly, this is really last year's technology, and they usually require one of these air trough fittings. They're not used as often. In most cases, if somebody has them, they'll convert them to a bladder tank or a diaphragm tank. Diaphragm tank is like a bladder tank. The only thing is it has a diaphragm over here. So instead, there's sort of like just a section of the bladder, and it just expands. The rubber just expands downward. Okay, where do we place the expansion tank? Well, the expansion tank is the point of no pressure change. Okay, the system pump should always be placed after the tank, so you're pumping away from the point of no pressure change. There's where the pump would always go. It's always pumping away from the expansion tank. Sometimes we also offer a system where, as you can see here, what's happening is this is a backflow preventer, pressure reducing valve. This would be connected to the line. We put the expansion tank here. Here's an air elimination device. And then we would put our pump, pumping away from this expansion tank. This is a complete system. It's great offered by one of our manufacturers, Xylem. Basically, it has it comes with an air elimination device, a nipple, an isolation valve, boiler fill valve, backflow preventer, and an expansion vessel suitable for a single boiler or single family home. Great device. We have these units, very suitable. So besides the expansion tank, the other device that we're looking into is a pressure reducing valve. We also sometimes call it the fill valve. When it's supplied with a relief valve, it's known as a dual unit, and it allows the installer to fill the system at the required pressure. They usually come set at 12 psi. If you recall, at the very beginning of the presentation, we said, hey, look, if you have a 20-story building, divide that by 2.20, two floor or a single family house, 20 feet up in the air. This is the highest radiation. Divide that by 2.31, which is about 8 psi. Add 4 psi to that, that's 12. That's why they come standard at 12 psi. As you can see here, once again, the pressure reducing valve here's basically the basic water properties. Raises at 27 feet. 1 psi divided by 2.31 is 4.33 pounds. So when we're setting the pressure reducing valve, we measure the distance from the height of the pressure reducing valve to the highest known point of the system. This is known as the static height. And then we divide by 2.31. As you can see, if it's 18 feet away, divided by 2.31, it's 17.79. We add 4 psi to it just to be able to push any air out of the way and make sure that we have positive pressure at the highest point. And that comes out to 11.79 or approximately 12 psi. If we have a larger building, we measure the distance of the height of the pressure reducing valve to the highest point of the system. That's the static height divided by 2.31. For example, here we have a 3-story building. That's going to be 12.55 psi. We add 4 psi to it, so they're going to have 16.55 or 17 psi. So after the system pressure is set and we fill the system, by rights, you really should shut off the valve before the reducing valve. Now, a lot of people say, well, what happens to the boiler from dry firing if there's a leak? Well, the PRV is not designed to protect the boiler. It's only to assist installing and setting the correct system pressure. The pressure is set. You have a low water cutoff on the boiler, which is by code on all boilers. That low water cutoff, that's what actually protects the boiler. If you have that open valve, what you're going to end up doing is you're going to end up having a flood. So let's look at some of the other components that you're going to find in a system. So we've covered the boiler, we've covered the pumps, we've covered the expansion tank, we've covered the pressure relief valve. Now let's take a look at flow or check valves. Why do we need flow control valves? Well, it's got nothing to do with controlling flow. What they really are there is to prevent overheating and crossover. See, inside a pipe, you remember heat rises and the hotter water is going to rise, cooler water is going to fall, okay? And this is going to happen even when the pump is off. You're going to have this flow, this gravity flow inside a pipe, even when there's no pumping. And what that can do is that can let the hot water migrate into zones that are actually off. This gravity of ghost flow, can occur in two pipe systems as well. And you can actually have a return that can be hotter than the supply. So the flow check valves, that prevents that flow from occurring. You put them in locations to make sure that you don't get this ghost migration. And Bell & Gossett has been making iron body straight angle patterns from 3/4 to 2 inch, a sweat brass unit for 3/4 inch, and an angled pattern of 2.5 and 3 inch, and a straight pattern up to 4 inch. So we've offered a wide variety of these gravity flow valves that have been used in systems extensively throughout this region and throughout the country. Then also what you can have is you can also have a check valve or a flow check valve. There are flanges that have them. And a lot of the pumps, they automatically come with them. Those new EcoCirc 2018s, they come with them, and so do a lot of other pumps. These check troll flanges have these flanges with the built-in check valve here on one side. They come in 3/4 inch to 1.5 in IPS and sweat. They're compatible with almost all pumps. Another unit that you can use is you can use a hydrotrol flow control valve. Those come in sizes 3/4, 1 inch, 1.25 inch. They can be a vertical or horizontal installation. And the next really important device on a hydronic component is going to be to eliminate air. You know, when you have if you've never noticed, if you have a bottle of soda, when you take it out of the refrigerator and it's cold and you open it, none of the air comes out. When the bottle of soda is warm and you open it up, it usually wants to overflow. So whenever you heat water up, the air has a tendency to want to escape. There's always air inside the system and it has a tendency to want to escape. So controlling the air is critical to hydronic systems. And Bell & Gossett makes a variety of devices. For residential devices, they make inline air scoops from 1 to 3 inches. They make enhanced air separators, which have a coalescing medium, which makes the bubbles and allow them to escape out of this air vent on the top. They come in sizes 1 to 2 inches, or they make these smaller units, these EASB juniors, which is enhanced air separators juniors. They come in 3/4 inch to 2 inches. So how do they work? As water enters the air eliminator, slows it down. The trapped air rises to the top and is released by the opening at the top. Here you can see a little cross-sectional view. Kind of shows you it's pretty self-explanatory. Flow comes in this direction. It's broken up. Has a tendency that those bubbles tend to rise to the top, allowing the water to come out, hopefully air-free. Another thing, larger devices, one of the things that we strongly recommend is also a primary secondary header. They serve two purposes. They they separate primary secondary circuits by acting as a closely spaced T, which is normally seen in traditional primary secondary piping. However, it does more than that. This product also acts as an air and dirt separator. The vessel is designed to create low velocity areas, allowing the air to rise to the top and then sediment to sink at the bottom. In a lot of cases, these are, especially if you have large systems with modulating boilers and primary, secondary devices, in a lot of cases, this is a much better alternative than putting another air elimination device in there. They work well, and they also take advantage of closely spaced T's and allow you to optimize the piping. It eliminates the need for setting the piping right, and it's generally speaking, a really good device. Comes with an air vent, comes with a drain valve, and it comes with an insulation blanket. Sizes are IPS from 1 to 1.5 inch and a flange from 2 to 4 inches. In addition, we also have custom sizes and configurations. Here's one that we had made specially for a job. This is made with Aquatherm polypropylene random. It's custom fabricated for this particular job to make sure it fit right inside the location that we needed it. Also, we have other manufacturers that make them to much larger sizes, 6, 8, 10, 12 inches as well. The primary secondary headers, here you can see an application where they use them. So what you have is you have this primary secondary piping, you have this closely spaced T's, the boiler pump is flowing in this direction, the secondary circuit is going to the radiation in this direction. So you have one path in this way, one path in this way. Instead, we can do the same thing. We can eliminate the need for this air elimination device by putting this in here and making sure that we have an undersized and have set the primary secondary circuit properly. In addition, we have a blowdown situation here for getting rid of any sediment in the system and an air elimination device of air vent on the top too. As you can see, so these are devices that we highly recommend. The other thing, another device that we have is differential bypass. So if you have what happens when the system flow varies due to zone valves opening and closing, and ensures that adequate flow remains in the circuit. It helps eliminate velocity noise by allowing excess flow to the remaining circuits. You don't really need these if you have ECM pumps or variable frequency drives. These are used more in older systems. Here you can see an application where this is being used. Here you can see we have a differential bypass valve put over here. And what this does is this connects this, what this is as these loads go on, this will pass the flow through here back to the return. If the differential pressure on this side of the device becomes greater because these have shut off and there's no flow going through these paths. So if there's flow going through these paths, this will not allow the water to flow in this direction. It's usually jumping the pump is what they say. Here we have a device, the triple duty valve, which is placed on the discharge side of the pump. It combines 3 functions into one device. This is why it's called a triple duty valve. It's a calibrated balancing valve. You can see here's the gauge here. It's a spring-loaded check valve, and it's an isolation shutoff valve. So this device serves 3 functions in one device. They come in a large variety of sizes, up to 12 inches, up to 14 inches actually, and flanged. They're grooved up to 12 inches. Straight pattern flanges from 3 to 16 inches, angle pattern valves from 2 to 10 inches. They make smaller ones too, like you see here, this brass device here with the handle, that's in 1 and 2 inch sizes. So what happens is as we look over a cross section of this, we have a calibrated nameplate here. A brass disc with a soft seat provides positive shut-off and a non-slam check valve. And then what you do is you have your integrated ports. If you need a delta, actually it should be delta P or a delta T measurement, a delta P measurement, so you can see what the pressure drop is across it. Those are used both in vertical inline pumps and also especially in end suction pumps. In addition, a lot of people don't feel they need them with the VFD, but in reality, if the system wasn't sized, was oversized, and I shouldn't say oversized, but if the designed flow and pressure drop for the pump was actually substantially, the pressure drop is actually in reality, much less than what was designed. In a lot of cases, the triple duty valve is the ideal tool to bring the pump back on the curve so the VFD can operate properly. Because if there is no pressure drop, the pump can then be running off the curve in a non. It doesn't matter what the VFD is going to do. The pump's already off the curve, so it's good to have one of these in line, even when there's a VFD on the pump. Another device that you want to use, especially on a end suction pump, is an end suction diffuser. What it does is conditions the flow of the pump suction to ensure the highest pump efficiency and retention. It enables the pumping system to function at most optimal performance parameters. Basically, they come in sizes from 2 to 10 inches. As you can see here, here's a typical application. Here's your suction diffuser, here's your triple duty valve, and here's your pump. This is an end suction pump. This is a typical application where you would use these devices. So next thing I want to talk about is, we have a system, we have a bunch of components in the system, and the question is going to be, well, what about the water quality? And one of the lines there's two lines that we represent. One is boiler mag and the other one is Sentinel. Now, there are chemical additives, that's Sentinel, and there are filters, there are magnetic filters. So in a closed loop and hydronic system, I mean, looking at these, look at the interior of these pumps, you can see all the buildup of scale and corrosion inside these systems and inside these pipes. And you can imagine what this is doing to the flow and changing the characteristics of the pump, of the flow through the system, regardless of what the pump is doing and the behavior of the pump relative to its original install. So you're going to have problems that you're going to cause general corrosion, you're going to have pitting corrosion, sludge, the buildup of sludge, biofilms. You can have blockages and scaling. I mean, these are going to cause failures, and it's going to reduce efficiency. It's going to increase fuel usage. It's going to create downtime, callbacks. It's going to make hot and cold spaces. You can have in poor quality water, it causes a reduction in the heat transfer rates up to 15% and 6% boil efficiency after only 3 weeks. This is what studies have shown. You can have low flow areas creating dead legs, regions of the system which are actually not providing sufficient flow and therefore can't generate enough heat in that area. Poor water quality will end up creating premature component wear, causes breakdowns of various components. And one of the things is that, in Europe, one of the things you cannot, your warranty is pretty much void on any boiler if you don't have water quality treatment. This is an excerpt from a Baxi Luna operating manual for the UK market, and in it, what you can see is that they talk about the treatment of water in circulating systems, and this is straight out of their manual. And it says there's all, one of the key things here, it says a suitable inhibitor must be added to the system. All systems have to be flushed and drained. using an appropriate proprietary flushing agent. So first, they recognize that there's corrosion inside all hydronic systems, and that'll create corrosion, sludge. It causes damage to the pump, valves, boiler noise, circulating problems. When new system fluxes be evident in the system, which can lead to damage to system components. This is a British standard, gives extensive recommendations on cleaning systems and water treatment. And all systems need to be thoroughly drained and flushed using an appropriate proprietary flushing agent, and a suitable inhibitor needs to be used. In addition, all system additives, flushing agents, cleansers, inhibitors must comply with the requirements of this British standard. Okay. Failure to flush and add inhibitor to the system will invalidate the appliance warranty. So they take it very seriously over there. And it's something that we really haven't been paying close attention to, but it's something that we really need to. So the system that we have, the Sentinel system, offers a lifetime protection for this hot water heating systems by cleaning, protecting, and maintaining the system. So in older systems, we offer a product called X800. It quickly reduces deposits and scale in roughly about an hour. It's a fast-acting cleaner, unrivaled chemical technology. It dissolves corrosive debris. It can work in cold systems and can also be used as a power flushing device. In newer systems, we offer the X300. These clean new systems up to 6 months old. It's powerful, heavy-duty cleaning action, gets rid of debris, washes off manufacturing greases, reduces flux residue, and prevents copper deposits from being left in the system. This prepares the system for protection using it for an inhibitor. Now, the inhibitor is the X100. They offer a rapid dose. It comes in either these rapid dose devices, gallon or 5-gallon containers. It's a unique twist and dose appliance and hands-free dosing for medicinal applications. 1 can is typically sufficient to treat a typical domestic central heating system. It's an easy dose design. It discharges into the system in 30 seconds. No need to depressurize or cool a system. Multi-location applications can be combined with twist and dose systems. It's simple to dose. One dosing adapter allows 4 simple dosing methods. The adapter also features a visible bullet, which prevents water from escaping the system and provides visible confirmation of dosing. As you can see the little bullet over here. I'll show you a little. You can see a little video to see how this operates. Okay. So, like I said, as you can see here, the X100, which is this inhibitor, it protects against lime and scale and corrosion. It's an energy saving truss recommended. It's a corrosive technology. It's pH neutral. It ensures optimal system for efficiency. It's suitable for hard, soft, and artificially softened water. As you can see, a lot of this product is actually required for a good deal in many boilers, and it's required in almost all of Europe. And we had the clean, which was the 800 for older systems or the 300 for newer systems. This is the maintain, and then we have the protect, and then we have the protect is the 100, and then the test kit level is for maintain. This is the maintain section. Test kit is a simple way. It's simple device where you just take a small sample, dip these in there, and they can tell you whether or not you have the proper protection. And these little strips will give you the right answers. So it checks the inhibitor level in a minute. And also, you know, the problem that today is this isn't your father's boiler. You have much narrower waterways, and these waterways can be subject to clogging. You have ECM pumps. Remember, they have a permanent magnet, and they have a low tolerance for a thing called magnetite. Essentially, as these heated water travels through iron systems, whether they be cast iron or iron pipe and the like, what'll happen is that magnetite or small bits of iron oxide will fall out of the system. If you've ever put in irradiant systems, you put in those nice clear pipes, you come back there 6 months later and there's black stuff all over the place. That is essentially the magnetite that has fallen out of the system. And this is a section out of a Lochinvar manual, and then it says in the installation section, it says install a field supplied strainer filter to prevent damage to the heat exchanger caused by debris from entering the system piping. Okay, common sense. Everybody's been doing that. When installing a pre-existing system, a strainer filter capable of removing debris left in the system is recommended. On the next line, it says, install a field-supplied magnetic separator in a heating system return line as close as practical to the boiler per the manufacturer's instructions. And they're really, these almost all boiler manufacturers are really looking for magnetic separators to be put in. Some of the products that we have, Sentinel makes these Vortex smaller units in 3/4 and 1 inch, which provide filtration. And take a look and see how this works. Okay, as you can see, but you know, those were only 3/4 and 1 inch. We can also offer boiler mag, which offers the same type of magnetic filtration technology up to 1.5 inches, and then the larger boiler mags from 1.5 to 12 inches for large systems. These devices really are essential in modern systems. The amount of magnetite that's in systems, the amount of corrosion that it causes, is pretty dramatic in these newer systems, especially with ECM pumps and these smaller water tube boilers, even fire tube boilers. They really require this to maintain them from corroding and breaking down prematurely. Okay, we've talked about many of the components. We've talked about water quality. Let's spend a little time on some piping concepts. This is what we used to do. So we had a compression tank up there, a flow check valve, an air control fitting, pressure reducing valve, and a relief valve, and then the booster pump there feeding back into the boiler. Here's what we should be doing now. As you can see, we have an air elimination device. Over here, we have our expansion tank, and the pumps are pumping away from the expansion tank. Also, we have our indirect hot water heater and check valves to make sure that we don't get ghost flow into the other zones. So what we have here is we have a number of ways that we can pipe. One is a one pipe series loop. Uses less pipes, less expensive. You can't zone without a bypass. It has larger delta T's. And one of the problems that you usually have to compensate for is radiators at the end of the loop are going to get a much lower water temperature than those at the beginning of the loop. A better alternative is a monoflow T system. What happens is you'll have a tendency to get equal delta T. The water temperature stays constant, and it's much easier to zone and control because you're continuing to flow water through there. And the monoflow T, also known as a Venturi T, how does that work? Essentially, as you can see here from this diagram, there's a Venturi on one end. The flow goes through there, and it creates a pressure differential, allowing the water to come out of the radiator. Here you can see what happens is that you have a regular T on one end, the flow splits, and then what happens is that the restriction here creates a pressure drop, and the water comes back in and flows through the radiator. A other method is a two-pipe direct return system. And this is going to use more pipes, more expensive. It's much easier to zone. The delta T will vary, and you may not get equal flow in the radiators. But a better alternative to that is a two-pipe reverse return. Now, what's going to happen here is, as you can see, the first one out is the last one back. That's reverse return. First one in, last one out. It's more expensive, it's easier to zone, has equal delta T, and the other big advantages is that it guarantees the radiators will all get equal flow. Now, that's a recommendation. Using this reverse return piping concept is something that we really recommend if you have multiple boiler applications. You really want to pipe these in. This reverse return. The first boiler going out to the system is going to be the last boiler coming back. Now, take a look at our near boiler piping system here's a simple diagram, standard diagram for a combi boiler. Inside the boiler, we have our boiler pump. This is flowing into a primary secondary header, goes back out. We have a domestic hot water mixing valve and our domestic hot water expansion tank, and our feed is going out to the system in this direction. On the system side for the heating, we have our pumps and our zone valves, and then our returns on the other side. Pretty simple system. Okay, notice up here we have our low water cutoff at the highest point to make sure that the boiler is protected and that it is guaranteeing that there's water in the system. Sometimes if that seemed a little complicated and somebody's looking for a simple or a standardized way, we offer what I would call a boiler in a box. So we do have these prefabricated headers. You can contact Wallace Innes and we can get these to you, and you can guarantee us, if, say, for example, if you're doing a multifamily application where you're putting combi boilers in each one and you want them all to be standardized, This will save time, installation money, good deal of cost over the life, and guarantee standardized installation for each and every unit. Let's take a look at some piping concepts here, some more piping concepts. What you see here is, once again, we have our primary, secondary header, a zone's going out, 2 boilers. Notice that this is the this one goes in here. This is the first one going in here, and the return. This is the, here you can see the primary, secondary header. You have 2 boilers, and the indirect you can see is being taken off as a zone. So sometimes you can do it on the primary side. In this particular case, we're doing it as a zone. These are fully in Lochinvar boilers. This is easily programmable. Here's another application, same thing. Notice the expansion tank is tied in to the base of the primary, secondary header, and all the pumps are now pumping away from the expansion tank. Here you can see another similar application where we have 3 units. Here you can see this is the first one in, is the last one back, and the last one in is the first one back. Here they reverse return pipe this. You can see over here, it's pumping away. Here's our expansion tank, and these are all pumping away from the expansion tank. Remember, the expansion tank is the point of constant pressure. Same thing here, similar situation here, also reverse return piping, just a different set of pumps. Now, in this particular case here, we've done this, we're using a buffer tank instead of a primary, secondary header. This would be applicable if, for example, we had some radiant zones and some like baseboard, fan coils, and we also had some, say, radiant zones, and the radiant zones were particularly small, say maybe in a vestibule. You would want a buffer tank because you wouldn't want every time there was a call for heat for these boilers firing constantly for that small zone. The residual water acts as a sort of a battery to provide the heat for provide some small amount of electricity instead of turning on the whole generator. Notice in this case, we have 1 domestic hot water indirect tank, and we're feeding it as part of the primary set of the circuit, not on the secondary side like we did on the other applications. Again, here we put our expansion tank over here so that the zones are pumping away from this expansion tank. Have an air elimination device here, and also here you see a domestic hot water expansion tank. Notice it's a much smaller tank than the hydronic tank because there's a much smaller delta T. Here you can see another system where we have a custom primary, secondary header, okay, a 4-way mixing valve feeding these larger pumps would return. This provides some protection and also gives us some temperature control in addition to the temperature control coming from the boilers here. Looking at this photo here, at this drawing here, you can see once again we have our expansion tank at this point here. We're pumping away from the expansion tank in this direction, away from the expansion tank in this direction. This is a simple wall hung boiler, primary, secondary piping. Okay, now here what you see here is a 4 crest boilers, some base mounted pumps, mixing valve, expansion tank, primary makeup during, and here's a custom primary, secondary header. Here you can see another application of a schematic application of that. Here's the primary, secondary header. Here's the pumps. Here are the boilers and a connection to the tank. When in doubt, it's really usually advisable to use a primary, secondary header if you can. Similar application. I don't have these, I'm sorry, I don't have the fonts on here for the description, but basically you got small pumps feeding the boilers, primary, secondary header, near burning piping. Notice again, first one in is the last one out, reverse return piping. Seem to see the same things over and over again. Reverse return piping, first one in, last one out, boiler pumping away from the expansion tank. Same thing here, and same thing here. It's standard situation. Now, a lot of times one of the things that's out there is thermostatic radiator valves. A lot of times we're looking to save energy on a building. You really can't replace a boiler room or change all the components. It's just not practical. But in a lot of cases, what we can do is we can put a thermostatic radiator assembly, which are non-electric, self-contained, self-radiating kind of zone devices, and simply applied. Here you can see you just dial in the set temperature, and the valve will automatically adjust to ambient changes in the air and control the flow into the particular radiator based on the ambient air temperature. Contrary to manual valves, thermostatic radiator valve assemblies, they save energy when the ambient air temperature rises, for example, in solar gain. Whereas regular manual valves will just on and off, these will have a tendency to really provide much more savings and much more advantages. The only thing that you have to consider, though, is that you really can't just have series piping, because what it'll do is one radiator shuts off, you won't get any others. So you need to use monoflow T's and temperature radiator thermostatic radiator valves. Here you can see a diagram, simple diagram here, where we're going into an air elimination device, continuous circulator, which is running during the heating season. And what they've done is they've had monoflow T's going into each one of the radiators, ensuring that if any one of these valves, any of these TRVs close, flow will continue through the other radiators and other heating devices. Here you can see if we have a manifold, that's just another option. You can always put a manifold in there and then run TRVs to each one of the radiators from there. It's a clever way of getting around doing things, instead of trying to putting monoflow T's everywhere. You can just run a simple manifold system. But if you're going to do that, you really need to consider putting that differential bypass device that we talked about before. That'll, when all of these close, it'll still have enough flow. Say if only one small zone is open and the pressure is too great for the pump, this will open up, allowing water to flow back to the boiler. Another thing is you can zone with parallel direct return. Once again, we had a 2-pipe system with parallel direct return. The only thing that our biggest concern here is that we have to make sure that the sizing of the radiation here is sufficient for handling the temperature. But as you can see, once again, they were differential bypass. Each one of these has its own valve. There's a heat emitter and then a balancing valve, because we need to make sure that we balance the flow to each one of these devices, that we're not running. If not, all the water is going to want to go through these early zones, and very little water will be going to these end zones. So we need some way of balancing out the system. One way to get around that, though, is to use reverse return. If we did it in parallel with reverse return, once again, the first one in is the last one back. It'll automatically balance out the system. And notice it's the flow is automatically balanced, and you don't really need it. You can get they're showing the valves here. There's isolation valves and a zone valve. You don't really need a balancing valve. You can just basically use a zone valve at that case. I mean, a isolation valve instead. Okay, zoning with primary, secondary pumps. Here you can see we have 3 radiator sections, and what we've had is 1 circuit, 2 circuits. This is our primary loop, And then using a mixing valve coming off, we have a much lower temperature. So we have three different temperatures: a high temperature secondary circuit, a medium temperature secondary circuit, and then a low temperature secondary circuit. Notice these are closely spaced T's so that the flow is gonna, your flow is gonna go across in this direction. So that's key to this. Also, the flow checks are key to this to make sure that we don't get gravity flow in the wrong direction. Here we go, zoning with zone valves, another option. What you can see here is you have an indirect hot water tank, and then we're zoning into each one of these with zone valves, which is going to cause us to have a differential bypass valve. Okay. One single circulator. Once again, our feed in each one of these zone valves does require us to use, we really need to think when all of these close what's going to happen. So that's where we come in with a differential bypass valve. What's more and more common today that I see much more often is zoning with pumps. One of these things here that they've shown is they've some circulator, they enter integral flow checks. These go out to space heating in each one of these pumps are feeding a specific region and a specific area. As you can see, a simple supply header feeding out return. It's actually, I see more people doing that nowadays than zoning with zone valves. Here you can see, okay, zoning with pumps. In any of these zoning situations, a lot of it has to do with, we need to have some level of control on the boiler. As these zones engage and disengage, the demand on the boiler is going to change. And paramount, one of the paramount programs in there is Lochinvar smart system. So as you can see, I mean, here you can see three different screens on the smart system. One is all's good. One is maintenance required. Here you go, Jones Plumbing and Heating, and their number is given. And then the third one is a lockout. So Lochinvar's front panels are color coded. They actually show you where you can see the temperatures on each, as a temperature control, where each one of the temperatures are at and the sensors are responding. What they do is they automatically have outdoor reset. Each Lochinvar boiler comes with an outdoor air sensor. It gives domestic hot water prioritization that's fully controllable, 4-pump control, boiler pump, secondary pump, domestic hot water pump, and a recirc pump. Also has freeze protection, runtime alarm contacts. There's a high voltage strip and a low voltage terminal strip. Time clock data logging, 10 data logs. So any of the previous failures are readily visible and can be through a simple touch screen. You can easily see what up to the last 10 failures were. That yellow screen that we saw a couple of slides back, that's the maintenance reminder. Also, low water flow safety control and indication, and it has password security to make sure that no unintended persons can change the programming of the boiler. The smart system is one of the finest control systems built into a boiler and on the market today. I haven't seen anything else that comes close. Cascade redundancy. Essentially, when you just need a twisted pair, shielded twisted pair. If you have an outdoor sensor, system sensor, and a heat demand sensor, what'll happen is if one of these boilers fails, the second one will automatically become the leader. So there's redundancy in Cascade. The Cascade system is up to 8 boilers. Just twisted pair is more than enough. Is only a shielded twisted pair. And on pretty much, it's available on all residential night boilers, FTXL boilers. It's standard on the Crest product is the Connexus. The Connexus is if you have a Wi-Fi signal in the building, the Connexus can then connect, and you can actually troubleshoot or service or read the controls remotely over the internet with the Connexus app, which is available free. The cloud service is free with the purchase of control, and like I said, it comes stock on some of the larger units. It's additional revenue for the installer, allows total remote access. It can be offered as an add-in. It'll can alert you if there's a failure on the boiler. If one of the boilers go down, if you have a building with 3 or 4 units and one of them goes down, it can automatically send out a signal, an email, or a message to you so that you know that you can get ahead of it. It's you know, it allows you, keeps you to the customer, keeps you linked to the customer, and provides peace of mind. I mean, in a lot of cases, you can solve many problems without ever having to make a service, you know, ever having to get out into the actual job site. Here you can see some of the basic screens here. It shows you the water temperatures, the delta T, the outlet water temperature, whether or not the flame is running, flue temperatures, premix temperatures, set point, what the status is, what's happening, where it's modulating at. So that's the Connexus is really powerful. It works hand in hand with the smart system and gives you full control of the boiler and the system as a whole. So let's take home some messages. Here, we're starting to wind down here, and let's go through a few key messages. So the rules of thumb. First of all, to determine the flow rate, you take the net BTU load, divide that by 10,000. That gives you the flow rate. The maximum flow rate for copper pipe, as you can see, the sizes: 1/2 inch is 1.5 GPM, 3/4, 4 GPM. That's standard. It's 40,000 BTUs. 1 inch, 8 GPM, 80,000 BTUs. 1.25 inch, 14 GPM, or 140,000 BTUs. How do you determine the pump head? Measure the longest rod in the feet, add 50% of that number for the fittings, multiply that number times 0.04. That's the pump head. That's how you get the head quick and dirty. Here, once again, I go the maximum heating carrying capacity. 1/2 inch should be 15,000, 40,000 for 3/4, 80,000 for 1, or 140 for 1.25 inch. Maximum length of fin tube baseboard. Typical baseboard would be, in 1/2 inch would be 25 feet. In 3/4 inch would be about 67 feet. 1 inch, if you had larger baseboard, 1 inch baseboard would be about 104 feet. 1.25 inch would be about 177 feet of baseboard, of larger 1.25 inch baseboard. The number of convectors that a pipe can serve, typical convectors are about 5,100 BTUs per hour on a 6 inch by 3 by 24 inch convector. That 3 units with 1/2 inch, 8 units with 3/4, 16 on a 1 inch, and 27 on 1.25 inch. Shared piping size is another important thing. So if you have, it's really looking at 1.5 inch is 22 GPM. We talked about these 4 already. 2 inch, 45 GPM. Notice that the 1.25 inch steel is 17 GPM, and 1.5 inch steel is 25 GPMs. 2 inch steel is 50 GPM. So you can keep that in mind. Those are key numbers to keep in mind. Here's another thing. So I would highly recommend using, if you need to do expansion tank sizing, and it's not something that you can use from the Simple Dirty book from provided by Bell and Gossett, you can go to XylemUSAsizing.com. This is a neat little unit. It's a simple way of doing it. It's quick and dirty, and it's pretty informative. You can either look it up on a chart, or you can actually put the parameters if you know what it is. You know what the initial pressure is, the initial temperature, the final pressure, and the final temperature, and you can use that as a means of sizing, especially large systems. And I can't also tell you, you really should consider Lochinvar University. for any questions. Here's a sample screen on the Crest boiler. Video tutorials, find the tools you need here, be our guest. I mean, all this. Lochinvar University is a really, really useful, very, has a lot of information. You can see the website here. It's basically lochinvaru.com. Also, Bell & Gossett has a remote learning hub that's right off the Bell & Gossett website. This is the sort of all the Bell & Gossett pages come up like that. You just click training and education and choose the remote learning hub. You can see also here's their web address, bellandgossettmarketing.com, schoolhouse. And if you're a Lochinvar installer, I could strongly advise you to join the Lochinvar VIP program. It provides rewards. It provides gifts for first of all, provides awards, contests, free gear, and also when you register the boilers, also there are rebates involved too. If you have any questions, just reach out to Wallace Ennis and contact your local salesman. We'll be happy to help you out with this. It's a great program and very, very, very nice, very well run program. Once again, at Wallace Ennis, we're team professionals. We're ready and willing to work with you, either system design, equipment selection, and troubleshooting on all of our product lines. We're here to call. Just checking to see if there's any questions, please enter the chat box.